Hi students, welcome to the session on relationship between the electric potential and the electric field. We know electric potential is V, electric field is E. We are going to see that only. Right, already we know V is equal to minus E dot dl. Right, so this gives, now we have to derive in another form, right? So how E is related to V. This is talking about V is related to E. So we see that dV, I differentiate both sides. Differentiation of integration means that integral will move away. So that is equal to E dot dl, right? So dV I write as dou V by dou x dx plus dou V by dou y dy plus dou V by dou z dz, right? Okay, that is equal to minus E dot dl. You see, why I write like this? This is a volume integral, right? So, sorry, differentiation of potential, right? So, potential means what I am, this is dV, I split, it is talking about space, free space. See, we find potential at particular point in the space. So, for example, we found this potential at this point, Vp. This is the origin, we have source charge kept here and the distance r. So, what I do is, I am taking this distance in the terms of x-axis this much distance you go, y-axis this much distance, then z-axis. So for example like this, right? What we do when we represent any point in 3 dimension, we need p of x, y, z, right? So x direction I move dou v, that's why it is dou partial. Dou v by dou x, how much distance it has changed in x direction. How much distance potential has changed in y direction. See how much it has changed in y direction. How much potential has changed in z direction. This is total potential change in the space. I split into 3 parts. Change of potential in x direction, change of potential in y direction, change of potential in z direction. Okay, so this I write as dou v by dou x ax plus dou v by dou y ay plus dou v by dou z az dot dx ax plus dy ay plus dz az. Why? When you take a dot product, you multiply the same unit vector. So a dot ax dot ax 1. So dou v, see first you multiply these two, right? Ax dot ax 1, dou v by dou x dx. Next you multiply these two, right? So dou v by dou y, ay dot ay 1. So dou v by dou y, dy. Next dou v by dou z, az 1. So dz. So that's what I represent this term, right? Okay. Now right hand side remains same. Okay. So right hand side is E dot dl. So I write E dot dl is total length in 3 dimensions. So I write as dx ax. This is a displacement in Cartesian coordinate we know. dy ay plus dz az. Okay. So now if we simplify, what we get is, this is nothing but our what? Del v. Yes or no? Right? So this is nothing but our del v, because del v is dou by dou v ax dx ax, dou v by dou y ay. Del v no. Del is nothing but dou by dou x ax, dou by dou y ay plus dou by dou z az. Right? So del v means v. So this formula is like del v dot, right? Dx ax plus dy ay dz is nothing but our dl. Right hand side E dot again dl. Now you see del v dot dl is equal to E dot dl means surely, so minus is there, please don't forget. In front of this minus is there, right? You see minus. So del v is equal to minus E dot E. This implies E is equal to minus del v. This is the most important relation. Why it is most important relation? We know E is a vector, so V is a scalar. It relates scalar quantity with respect to vector quantity. That is the beautiful concept, right? Right? So you see, gradient is the parameter which relates. What is gradient? It will give maximum change. Change implies it has both direction and magnitude. In which direction it has changed, and it has in how much it has changed. So maximum change of potential. So electric field is negative of potential gradient. V is potential. That's why it is a del V is nothing but gradient of potential or potential gradient. See, what is potential maximum change? Already we studied. Electric field goes in the direction of decreasing potential, right? You see, maximum change in potential, but in the negative direction. That is decrease. That means high to low. You hope you remember this point. You see, for positive charge, we told, right? Closer that it's a VA point, let us assume it's a VA, this is VB, point B, potential, where electric field lines will be moving away, right? So you see, where is the potential? Potential A will be higher than B. Electric field lines goes in the direction of decreasing potential. So E will go in the direction of decreasing V. See, electric field goes, potential gradient means maximum rate of change in the opposite direction. That means decreasing potential. That's what E is equal to del V. That is related here. Very important point. Right? Another thing you see for negative charge, we draw a line like this, right? So we know for negative charge, closer that potential will be least, higher point potential will be maximum. Here also you see electric field goes in the direction of decreasing potential. Here VB is greater than VA. Again, E is equal to minus del V. So I don't need to work with E. If I know E, I can know what is V. By using this equation, E is equal to minus del V. Right? Okay. Now, already another point we know, E dot dl is equal to 0. Right? If you substitute E is equal to V, E is equal to minus del V dot dl is equal to 0. What it is implying? Algebraic sum of, or algebraic sum, since it is integration, again it is sum only. Algebraic sum of potential drop because decreasing potential around any closed loop. Why it is? This is closed. Any closed loop is 0. What is that? It is nothing but our KVL. So this equation is known as point form of KVL. Very important to mark. Right? So point form of KVL is the most crucial question, right? Okay. So electric field goes in the direction of decreasing potential, right? So next, so E is equal to minus del V is saying, right, how fast potential vary with respect to field. How fast V varies, right, in the field. Because del is telling rate of change of potential where in the field. Okay, that is very important point to be noted. Simply potential is nothing but potential energy per charge that we studied. Potential energy per charge, whereas electric field is force per charge, that is electric force per charge. Fine. So this is another important point. Next thing we have to know is electric potential due to system of charges. Potential due to system of charges. So far we studied we are having one potential at origin and we want to find what is potential at point P, that is potential P, the distance is R, we know. But it is only one charge. Suppose the world is full of charge, not only one charge. Suppose we are having n number of charge, all the charges will produce potential at point P. So let us assume this distance is, okay, I draw neatly, Q1, so Q2, right? The distance between the potential point and this one is R2, this is R1. Let us take another one charge located here, that is Q3, the distance is R3, like that n number of charge Qn, Rn. Right? How to find a potential at point B? It is due to the sum of individual charge, like electric field due to the system of charges. So V total is equal to potential from charge 1, potential generated by charge 2 and potential generated by charge n. Okay. So what is V1? V1 is KQ1, potential due to charge 1. KQ1 by distance is R1. V2, the KQ2, the distance between the charge and the potential point is R2. Like that it will go Vn, sorry, right, KQN divided by Rn. This implies I can take outside. So V is equal to K into, right, so K. Right, K is nothing but 1 by 4 pi epsilon naught summation I goes to 1 to n Qi divided by Ri. Right, so this is the potential due to system of charges. Right, so this is another important topic we have to remember. So that's all about this session. If you're having any doubt, please ask me in comment section. I will clarify all your doubts. Thank you.